Welcome to lecture 15 of CS420. In this lecture, we're going to build our interpreter. Now, the reason we're building an interpreter is so that we can understand how programming language features work or what they mean. And this is called operational semantics. Because we're actually programming what it means for a certain feature, say for instance call by reference, which we'll talk about later, by programming it, we'll understand exactly what it means when we do call by reference. Now, the interpreter we're going to be building is an interpreter for the extremely easy language. So that's the new language we're going to build. Now, we're going to write this in YACC. So there's two programming languages. One, the programming language used to implement the interpreter, that's YACC. And two, the programming language that we are creating, which is extremely easy language. Now, the interpreter will have three pieces. The first piece will be the parser. Now, the parser is broken up into two separate parts. One is called the tokenizer, and the other one is the parser itself. Now, the tokenizer's job is to break apart is to read in our program character by character and break it apart into tokens. So it'll combine a word together or a number together. It'll take a parenthesis or a curly brace, and it'll call that one token. Now, once the parser has parsed it and created the abstract syntax tree, so you've had a previous lecture about abstract syntax trees and parsing, that's basically what we're doing. Then the interpreter itself will execute the code. And in order to store the variables, we'll also have the environment. Now, that's the same thing that you've had a couple of lectures ago when you learned about the environment, that we have an empty environment, then we can extend an environment and look up something in the environment. And so most of this lecture, we're going to focus on this interpreter. But first, we got to figure out our parser and expand that so that it can handle all of our expressions that we're going to have in our language. So we're going to be using a program called YACC to create our parser. Now, YACC stands for Yet Another Compiler. And you can look up on the web more for that, but basically we just give it our grammar specification, tell us what our language should look like, and it will automatically generate us a parser that will take our concrete syntax and turn it into an abstract syntax tree. So we just need to tell it our grammar. Now, the first thing is for the tokenizer. It's also called a lexical analyzer, and this is what's going to separate out tokens. And a token is like one word or one symbol that means something, like a parenthesis or a curly brace. Now, we can see here we have white space right here, and we're just going to skip over the white space. Then we have comments. Whenever we have a percent sign, anything after the percent sign will be a comment. Now, this no stands for arbitrary number of, so that means anything that is not a new line, it will just kind of add into the comment and skip over it. Now, we're skipping over white space because our extremely easy language will not have syntactic white space, so it's not like Python, Java, JavaScript, C++. They're all languages that do not have syntactic white space, and they just skip over it. Now, an identifier is any variable name. Could be a method name, could be a variable name, and it basically has to start with a letter. After it starts with a letter, we can have any number of letters, digits, underscores, hyphens, or question marks. So basically the lexical analyzer, the tokenizer, when it sees a letter, it'll kind of keep adding, it'll keep reading characters until it sees something that's not one of these, and then it will take that, call it one token, and say that it is a symbol. Finally, we have a number. A number starts with a digit and followed by an arbitrary number of digits. So obviously this specification right here will not be able to handle floating point numbers with a decimal point in it, but we're going to go for an extremely easy language that doesn't have that in it to simplify things. So that's all we need for our lexical spec. Now, I doubt in any of the assignments that you'll be asked to edit this, or it'll be fairly straightforward if you do. But this just basically tells our computer how to tokenize, or it tells YACC how to tokenize our concrete syntax. The grammar we will be editing more often, so you should pay attention to this a little bit more, but it's also a little bit easier to understand, and there'll be a lot of examples that you can draw from. Now, every programming language has a grammar, and that is what you have to follow to type in a correct program that does not have syntax errors. So the grammar for our extremely easy language is going to start off pretty simple. We have a program, and a program is just an expression. An expression is either a number, which is a literal expression, a symbol, which is a var expression, or a primitive expression that starts off with any primitive. Then we have a parenthesis. Then we have 0 or more expressions separated by a comma, and then a closing parenthesis. And then finally, we have our primitives that could be plus, minus, multiply, add 1, subtract 1. What that means is our programs can be just a number. So if we have just a number, then like 5, then our program, when we run it, will give us 5. It can also be a variable expression. And by the way, a number is called a literal expression. A variable expression, any variable, we look that up in the environment, whatever it's bound to, say 10 for x, then then our program will return the number 10. Finally, we have our primitive expression, so any primitive. So in this case, I chose the plus primitive. And then we have a list of expressions inside, which are the operands to our primitive. So in this case, we can put a literal expression inside of it, or a varref expression, and we can include as many as we want. There's no limit on that. Of course, when we implement our plus, we're only going to pay attention to the first two. But as far as our grammar is concerned, we can keep adding parameters as much as we want. So up here, we can see the very first thing, we have a program that's just an expression. An expression can be one of these three things. If it's a number, then that's a literal expression. If it's a identifier or a variable name, then that's called a var expression. And a primitive, which could be any one of these right here, followed by a parenthesis. And we have a separated list of expressions, and they're separated by a comma. And then we have a parenthesis at the end. And when we have one of those, like this right here, then that's a primitive expression. Now, we know from our lexical analyzer that it's going to skip over all the comments. So if we use a % afterward, this is a comment, and it will ignore the rest of that line. Now, with just this, our lexical spec and our grammar defined, we can use the SLL gen, which is YACC, and that is included from the EOPL library. We can use that to make our parser. And we have this function called scan and parse that it uses. We just wrapping this up there, and notice we pass the spec and the grammar into it. And basically what scan and parse will do, we can pass it a string, which is our program right here, and it will parse it. And if you notice, we have our literal expression with 5 inside of a program expression right there. So this is the abstract syntax tree. So we've gone from our concrete syntax to our abstract syntax. And hopefully you remember from a previous lecture when we talked about parsing and abstract syntax trees what this means. By the way, it does define the data types like we did in that lecture. And if you want to see the data types that our YACC creates for us, we could just go show the data types. Now, you wouldn't really be doing this much unless you're trying to debug why your grammar isn't acting the way it is. But you can see that it basically ran this defined data type. So we have a program data type, and we have an expression data type, and we have a primitive data type that YACC automatically created for us. And then when it parses our program, it goes ahead and creates those or instantiates those structs to be able to store our abstract syntax tree. Now we can parse other programs as well. So we just have a variable expression in our program, and you can see that it parsed it. We have a program whose expression is a variable expression. In this case, we have a primitive expression. The primitive is plus, and it's adding a literal expression to a var expression. You could see those built inside of our abstract syntax tree. And finally, we have a little more complicated primitive expression. We have a plus expression that's going to add a var expression right here to another primitive expression. And in this case, the primitive expression is going to subtract a literal expression from another literal expression, one with 10 and one with 1. So we could see that scan and parse takes our concrete syntax, or a string that's our program, and parses it and turns it into our abstract syntax tree. Now with that out of the way, we're going to go ahead and put our environment in here and start working on our interpreter. Now this environment code is mostly just copied from lecture 12 when we talked about environments. But basically there's 3 different functions. We have an empty environment to create an empty environment, a way to extend an environment, and a way to look up a variable in an environment. So if you don't remember, go review lecture 12 where we talk about these 3 functions. Now, there is no way in our programming language right now to declare new variables. So if we can't declare new variables, we can't have variable references where we look them up, or else we'll always have undefined variable. So just to help us out, when we will create an empty environment first, and then we'll automatically extend it with 3 variables, I, v, and x, I being equal to 1, v being equal to 5, x being equal to 10, just like Roman numerals. Now, one slight difference between this implementation and the implementation in lecture 12 is we are using vectors to store our values instead of lists. But that shouldn't concern you, because hopefully what you learned from lecture 12 is it doesn't matter how we implement it, more that we just know the API or the functions that we use to call to do our 3 operations: create an empty environment, extend an environment, and look up a variable in environment. The implementation shouldn't matter much. And in fact, we probably won't be changing this code very much, at least initially. Now that we have our environment in our code, let's move on to our main implementation of the interpreter. And this is where we'll focus most of our attention. Now, just to get our programs running, we define a new function called run that takes a string in for input. We're going to scan and parse that string, turn it from concrete syntax to abstract syntax, and then we're going to call eval program. An eval program will look into our abstract syntax tree and evaluate the program and return the result of that. So there is another function called read eval print, which I'll show you this working as well once we get our interpreter built. And that function creates a read eval print loop, much like the command line that we have, or our interactive interpreter we have for Racket down here. It creates one for our extremely easy language. So eval program is a pretty simple function. It's just going to do a cases, and if you remember the lecture where we introduced defined data type, the way that we get the data out of our abstract syntax tree is with the cases. So there's only one kind of program that we have, and it has an expression inside of it. So we're going to evaluate the expression, or the body of our program. Then we're also going to pass on that initial environment. So remember, the initial environment, it starts off as an empty environment, but we add I, v, and x into it. So this environment has 3 variables that are bound that are like global variables in our program. So now we're going to write eval expression, and this is where most of our programming will happen. And this follows the 5 steps of recursive programming. Remember, step 1, write one expression or one function for each non-terminal. So we have one for eval program, we have one for eval expression, we'll create one for primitives later on. And now step 2 is to separate out our production. So which kind of expression do I have? In cases, we'll do that automatically for us. Now, if we don't have an expression in there, then it will automatically error for right here. Now this isn't an error of the programmer, this is an error of us, because that means we've defined an expression using our grammar up here, but eval expressions down here doesn't handle that kind of expression. So now we'll go ahead and implement the first expression. Our literal expression. So a literal expression is one that has a number in it. We'll call that number datum. And the result of evaluating a number is just returning that number. So that one is pretty easy. So we'll go ahead and run that. And now we can go ahead and try to run an expression. So if we have an expression with 4 in it, we see that we get 4 back. Now that doesn't seem too remarkable, but what happened is, first of all, 4 got parsed from its concrete syntax into an abstract syntax tree. Then eval program got called, and then eval expression got called, and it said, what kind of expression is this? Oh, it's a literal expression, and it returned 4. Now, I just want to show you what happens if we run a var expression. In this case, we don't handle that kind of expression yet. We'll add that next. But we'll run into this else thing, this else clause, and that will print out an error message. And now remember, this means that we have not handled the case where they have var expressions. So we can add var expressions next. So in this case, when we have a var expression, we're given some sort of identifier. Now what we want to do is not return that identifier. When somebody types x in, they don't want x back. They want to know what x is bound to. So we'll use our environment, and we'll pass in the environment and our variable name. It'll look it up in the environment and return us the value of that. So let's go ahead and try to run that. Now remember, our initial environment, just so we have some variables to look up, includes I, V, and X as global variables. So we'll go ahead and run a program, say X, and we get 10. Then we can also do V, and we'll get 5. And we'll also do I, and we'll get run. And now what if we do a variable that doesn't exist, like T? Now our apply EMV will print out an error saying no binding for S. Now this is an error that you might be very familiar with whenever you misspell a variable. It says undefined variable. This is another way of saying undefined variable T. Now we'll handle the last case, which is a primitive prim app expression, or a primitive expression. In that case, we have our primitive, plus, minus, add 1, subtract 1. And we also have our operands. Now, our operands are expressions. So this is a list of expressions. And when we make our interpreter, whenever we have something that is plural, that means that there's more than one. And that means we probably are going to have a list. So what we need to do is we need to recurse. Remember those 5 steps of recursive programming? We've broken this apart, and now we have a list of expressions, and we want to evaluate each expression and get a list of those expressions back. So the way that we'll do that is by the use of a helper function called evalrand. So evalrand will take in a list of rands, or a list of expressions, and an environment, and it will call eval expression on each one of them. So this could be just a normal recursive function that we've always written, and let me make sure I include my lambda here. A normal function that we've always written that does if our rands are null, then return an empty list, and if not, we could call eval expression on the car of the rands with our environment, and then recurse on the cutter and call eval rands on that with the environment. And that will evaluate each operand, or call eval expression on each operand. So from now on, when I say evaluate an expression, what that means is call evalrands, and we better have an environment to evaluate it in. So the last step would just be to combine these two results together, the result of evaluating the element of the list with the result of evaluating the rest of the list, and we combine those together with the cons. So that will do the trick, and would work for us, but we're going to use a slightly different method, and it's called map. And map is a good function to learn what it does. So in order to do that, first I'm going to create another function that is called evalrand, and it will take in an operand and an environment, and it will just call eval expression on the operand in the environment. So yes, we could just have this, instead of call evalrand, of course you could just call eval expression. So we can also do this and call evalrand. Now why would I do this? Well, maybe in the future as we add to our interpreter, we might want to do something to our operand before we evaluate it. And this gives us a little place to do something to our operand. And that is going to be when we study things like call by reference and call by name and call by need. We might want to add in some code before we evaluate the operand. But in this case right now, we just automatically call that. Now, this recursive function works just perfectly fine, but there is a slightly smaller function called that we can make that does the same thing, that uses map. And what map does, and if you notice our function, this is what the body does, it calls map. Now what map does is it takes in a function and a list. Now remember, rands is a list of expressions. So map takes in a function and a list, and it calls this function on each element of the list, and what it returns is the result of calling that function on each element. So you could see that basically this is a function that takes in one parameter. It calls evalrands with that parameter passing in the environment. So this function right here and the previous function I just replaced with this do the exact same thing. But map is a fairly common function in functional programming languages, and it's even made its way into a lot of iterative languages like JavaScript and Ruby and Python and some other languages that have functional features. So map is a pretty important function to learn what it does. So now just so we can see what evalrands does a little bit more, what I'm going to do first is primmap expression. When we have a primmap expression, we're not going to evaluate the rands. I'm just going to return them. That way we can see what they look like. So when I run plus 8x, let's see what the rands are. Notice it's a list with two expressions inside. One is a literal expression, 8, and one is a var expression with x. And so we can see we have a list of expressions. Now these expressions are in abstract syntax tree form. And so now let's find what happens when we call eval rands on our rands with an environment. So eval rands takes two expressions. So we'll run this again. And we can see what we get back is the result of evaluating those two expressions. So evaluating 8, which is a literal expression, gives us 8 back. Evaluating x, which is a var expression, looks up x in our environment, figures out it's equal to 10, and we get 10 back. So map returns those two evaluated expressions in a list. So we had a list of unevaluated expressions. Evalrands evaluated them and gave us back a list of evaluated expressions, or the result of running that code. So now we don't just want a list of our evaluated rands, we want to perform the operation on it, or this primitive. So now we'll let the args equal the result of evaluating the rands in the environment. So now args will be a list of evaluated expressions. We'll have their values back, and then we'll just have a little helper function called eval primitive that will figure out what kind of primitive we have, and then it will perform that operation on those arguments. And here's this helper function. So it will take in the primitive and a list of evaluated arguments. And by the way, evaluated arguments are called expressed values. Expressed values is what eval expression returns. So we don't return the abstract syntax tree. We return the result of evaluating that. Now, right now, our language only has one type, numbers. So eval expression is always going to return a number. But we'll add to that in the future. So now we have apply primitive. We'll figure out what kind of primitive it is. If it's a plus primitive, remember args is a list of expressed values. So we'll add the first one to the second one. The subtract primitive will take the first one minus the second one. The multiply will multiply the two of them. The increment will only look at the first argument, so you should really only have one argument, but it will add one to it. And the decrement will subtract one from it. And so now when we run this, and I just got to make sure I match up my parentheses so that this should close up here. And I think I have an extra parenthesis there. And going down, yeah, we got it all closed. So when we run that, eval primitive is bound. That means I should probably call it apply primitive up here instead. And now when we run this, we can run plus 5x, and we get 15 back. So evaluating 5 gives us 5. Evaluating x, we look up x in our initial environment, and x is bound to 10, so that gets 10 back. 5 plus 10 is 15. Now we can also do the read eval print loop, which will give us this, and now this is like a interpreter or a interactive interpreter for our easy, extremely easy language. And we can just go 5, and you see it returns that. We can look up a variable. We can do plus 5, 6, or we can do plus 5 minus v, make sure we put a comma in there, minus v8, and do that, and it evaluates, and we get the right answer. And to get out of it, we just click that button. It kind of gives us a little error-like looking message, but that's okay. And there we go. We have our basic interpreter. It doesn't do much. It just does some mathematical operations, but it's a good start. And with not a lot of code, we have a good base to create a programming language. Eventually, we're going to add enough to this language where we will have a complete programming language, or a Turing complete programming language, meaning our language can execute any program that's ever been written. We can evaluate that. Now, it might not be the prettiest, or it might take us a lot of work, but our language will be a Turing complete language.